G'day everyone, welcome to Lubrication Explained. In this video we're going to talk about PAGs. We're going to talk about PAG synthesis and PAG properties as well as the challenges associated with PAGs. So to get started we need to talk about an epoxide. So this is kind of like the building block for our PAG, and the definition is a cyclic ether with a 3-atom ring, and it kind of looks something like this. So this is what a generic epoxide would look like. You've got oxygen, which is bonded to 2 carbons, and off those carbons you've got 4 alkyl groups. As far as the building blocks go, we need to know about ethylene oxide. So that is the simplest of all the epoxides. So that's a cyclic ether with, just hydrogens coming off. So rather than the 4 alkyl groups, you've just got 4 hydrogens coming off the carbons. The slightly more complex version of that is propylene oxide, okay, where you have kind of like that methane tacked onto the end. Right, so these are the building blocks. You've got EO and PO, so ethylene oxide and propylene oxide. And a polyalkylene glycol, also sometimes known as a polyglycol or a PAG, is when you take one of these and you polymerize it. So in this instance, we've got a PO epoxide. If I just add more of them and start reacting them together to connect them all up, now I have a polymerized PO epoxide, which I would call a PO PAG. Now, it's probably a little bit more helpful to use kind of like a ball and stick model for this one. So this is what a PO epoxide would, a PO PAG would look like, and this is what an EO PAG would look like. Now, one thing that you'll notice about the EO PAG is that it has these oxygen atoms scattered all throughout. So basically every third atom on the chain is an oxygen. And that gives it some pretty unique properties. So we've spoken about polarity in the past. And one thing you'll notice here is that because the oxygens like to hold on to their electrons, there is kind of this net charge across the molecule. And so that gives it the capacity to form hydrogen bonds. And this is why EO PAGs are what we call water-soluble PAGs, very commonly used in things like the cosmetics industry, as an example. And they tend to take on water because they like to bond with it. That's obviously not really something that we want in the lubricant industry. So how is a PO PAG a little bit different? So these are more widely used in the lubricants industry, and you might say, well, hang on, I'm looking at the picture that you've got here, and it's the same oxygens up top. Shouldn't it also be polar and want to hydrogen bond with water? And you would be right in saying that, except for the fact that when you actually construct a PO PAG, it actually looks something more like this, right? So they sort of, the carbons alternate on the sides of the oxygen. And what that means is that if you look across the molecule, it's effectively symmetrical, right? And as a result, there is no net dipole moment across the molecule. That makes it non-polar, right? And it means that water is unable to bond with the oxygens. Partially because, like we said, there's no net dipole, partially because you've got all these hydrogens surrounding them, which are kind of hindering the waters from interacting with them. Right, so that's what makes a PO PAG what we call an oil-soluble PAG. And sometimes they're commonly known just as OSPs. Alright, so if we go down to our PO PAG and we make it a little bit longer, now when we look at the structure, we can get an idea for some of the physical characteristics of PO PAGs. So as an example, PO PAGs have excellent lubricity and therefore very low traction coefficients. And so you can see that if I slide these molecules past each other, because they have such regular structures and they're all quite flat and they don't really have any branched structures coming off them, at an atomic level they're going to slide past each other very, very readily and therefore have very low traction and very low, if you like, internal friction. So this gives them incredible lubricity. One of the other things as well is that they are incredibly oxidatively stable. Now, why would that be, let's say, compared to a PAO? Well, if you look across the hydrocarbon chain, there are oxygens all throughout this molecule. Now, what does that mean? Well, if you remember our basic definition of oxygen as being the gain of oxygen atoms, right? If there's already oxygen in it, it means that there are fewer sites where oxygen can attack, right? Because the oxygen's already there. So that makes them very oxidatively stable. Now, there's also the issue of solvency. So we already talked about the fact that it is a relatively non-polar molecule, right? So that in itself makes it an oil-soluble PAG. But there is something else to it as well. So if you look at an individual oxygen atom within the PAG, right, they want to hold on to the electrons more so than the carbons do, right? So that in some ways gives the oxygens within this structure a net kind of negative charge in comparison to the rest of the molecule around it. And so that means that the PO PAGs are able to solvate polar molecules within the bulk oil. And that's specifically really good for things like additive solubility, but also deposit formation. Because when, if you remember, deposits are byproducts of the oxidation process, they are almost always polar molecules. So as this PO PAG oxidizes, right, it is going to be able to absorb those oxidation byproducts. They won't fall out of solution and they won't form deposits. PO PAGs have another really cool trick up their sleeve, which is that when they oxidize, and I'm going to do this on the end of the molecule just for ease, right, what they do is they form an ester. So this functional group here, where I'm showing the oxygen with the double bond connected to a carbon which is connected to another oxygen, that is an ester functional group. And what do we know about esters? They are extremely high solvency molecules. So it means that even when a PO PAG oxidizes and degrades, it still has very high solvency, and so is therefore able to, in some ways, kind of clean itself. Alright, so what else do we know about a PO PAG just from this picture? Thermal stability is really good. So what happens with a PO PAG is that when it, at really, really high temperatures, if you thermally crack the molecule, it just breaks into very, very small polymers. And these tend to be so small that they actually just volatilize off, so they kind of vaporize, and which means that they don't really affect the bulk properties of the PAG. Now, if we go back to the picture of an EO PAG, right? Remember, it has some properties that we like, but it isn't oil soluble. So if instead we combine these two, we would have what is called an EO-PO PAG, where one half of the tail has better lubricity, right? Because if you look at it, it's even more regular, right? And it also has what we call some EP in it. So EP is not really something that we've explored in the videos yet, but it relates to extreme pressure. And if you remember from the video about anti-wear additives, it needs to have some polarity so it has an affinity for metal surfaces. And here, with an EO PAG, with all those oxygens up top, it has an affinity for metal surfaces. On the other side of the molecule, you'll then have the PO tail, which enables it to be oil soluble or oil miscible. So you kind of get the best of both worlds. Now, what's the catch? Because the way I've been talking about PAGs, it seems like they would solve all our problems. Well, there's a couple of issues. First is seal compatibility. It really sucks. Second is paint compatibility. It also generally sucks. And finally, you've got oil compatibility, which sometimes also sucks. So they don't play well with seals, they don't play well with paint, and they often don't play well with other lubricants. So that can be a really problem when you introduce a PAG onto your site because it doesn't play well with anything else. Now we can fix that a little bit through some of these kind of blending techniques. So as an example, right, if instead of a EO-PO PAG, we had a PO-BO PAG, which is a BO would be a butylene oxide PAG, right? What we can actually do is have something which is even more oil soluble than a PO pag, right? And that might help us with, for example, compatibility with other lubricants. So PO/BO pags, generally across the board, I think with the exception of some PAOs, but they have pretty good compatibility with all the other base oils. So that's something to look out for too. All right, I know that's been pretty high level, and we still need to talk about the applications of these base oils, mostly in gas compression, but increasingly we're starting to see it in gas turbine work as well. But if you have any questions or comments below, please leave them down below. Otherwise, as usual, this has been Lubrication Explained.